Okay, welcome back. Let's continue onward. So in the last lecture, we were talking about tracking systems, and I mainly covered the case of orientation-only tracking. This is very useful for a fully portable virtual reality headset, and where you're completely relying on inertial measurements, inertial measurement units, which gives you gyroscope readings and accelerometer readings, and magnetometer readings as well. And as some of you have asked, don't you also need to take into account the position of the head? So if you do a motion back and forth like this, or in general if you're tracking other rigid bodies such as your hands, then you would like to have position as well as orientation. So we talked about different cases, and remember we were mentioning that there was the case of line of sight visibility. That was the thing we finished on last time. So we have visibility or line of sight. You have some features that are in view of a camera, and then you would like to figure out where these are in the scene. So this leads to a very generic and well-studied problem called the PNP problem. The first P stands for perspective, which is just a model of the camera projection. Remember that I said for each feature that you can see in the world, this corresponds to, as it strikes through the image plane, a ray that you can narrow down that feature to in the world frame. And then the second P corresponds to points. So perspective n points problem. Determine the rigid body transform, the same transform we've been doing all along here, from identified, observed features on a rigid body. So in other words, I start with a rigid body. So let me go back to this cube head that I had before. So I may have particular features on here, and perhaps it corresponds, each one of my features may correspond to a corner of this. Right? I could imagine putting a bright LED on it, and then based on where these LEDs appear in the image, I have the problem of this figure, or this rigid body has moved somewhere. I want to figure out what its position and orientation is. What's given to me is exactly each one of the LEDs. I know the coordinates of the LEDs in the body frame, and I also have labels for them. This is LED number 1 maybe on this corner, there's LED number 2 on this corner, and so forth. I have labels on all of them, and when I see them in the image, I can recover the labels. That's what identified means. So how can this be done in practice? Well, I could have different colored LEDs, right? That'd be one way to distinguish them. Another way to do it is to have them flashing in some way and make some kind of code over time. So if I see them in multiple frames, they could flash between a light mode and a dark mode. So they could switch between two different frequencies, and you could get some kind of coded signal to identify them over several frames. So things like that could be done. Let's think about different versions of this problem, and I like to talk about degrees of freedom. So how many degrees of freedom do we have for the rigid body before we see any features? 6, full 6, right? All right, so I guess I could say that if we just have P0P, right, n is the number of points. So if I have 0 points seen, then I guess I remain with 6 degrees of freedom for the object. If I observe a single point in the image, I just want to reason about the degrees of freedom now. So for example, I have this object, right? And I can state that one feature is fixed. Let's suppose it's this corner. So I've observed this corner, I've identified it in the image. So the question is, what can this object do now while keeping this corner fixed in an image? How many degrees of freedom have I lost? Have I lost 3? Let's see. So can I do any rotation of this now? Not any rotation, because this would be blocked, right? But let's just say in terms of degrees of freedom analysis, we just do small perturbations. So I should be able to do any yaw, pitch, and roll. So that's 3 degrees of freedom, still intact, correct? But what if I make this thing closer or further from the camera, moving exactly along the perspective projection line that goes to the point? Can I do that too? Yes? I think I can do that. So that leaves 4 degrees of freedom for this. So what's changed is that this one point, did I get it right here? This one point can no longer go this way and can no longer go this way because it's been fixed by the pixel in the image. So in some sense, you can imagine the ij coordinates are the 2 constraints, right? The ij coordinates of this point in the image are the 2 constraints. Each one of those drops a degree of freedom. So that means that there are 4 degrees of freedom left after 1 point. So what about perspective 2-point problem? How many degrees of freedom are going to be left? Who thinks there's a pattern here maybe? So if I hold 2 points fixed, maybe I take these opposing corners here and say that they're fixed. I don't know if I can hold on to this very well. So I guess in that case, it looks like I could spin it like this, right? Is that only 1 degree of freedom remaining then? Yeah, it's somewhat difficult to see, but I should be able to also do some kind of transformation where I move this back and forth so that the angle between the 2 rays here, right, that stays fixed. So I'm kind of as if these two features are moving along rails, right? And I can go further back while reorienting this, and that's another degree of freedom. Does that seem okay? You know, try it at home with your own setup. Maybe I could do it here with a piece of chalk if I just. So it's like this. And it should be, yeah, I have it like this, right? And I can go like this, correct? Right? So that's the extra degree of freedom. Try it again here. Make sure you get that. So I could go like this. All right, so we get this extra degree of freedom. So that means there are 2 DOFs left here. So we go to P, 3P, and as you might imagine, we're down to 0 degrees of freedom remaining. So there are no more degrees of freedom remaining. And in that case, I have a picture that looks something like this. Imagine a rigid triangle that has the features on the corners, 1, 2, 3, and then these are all being observed in some image. So I'll try to make these lines all meet here. So there's an image plane where these are being observed. So I get these 3 points observed in the image. So somewhere in here, there's an image. All I'm really imagining is the detection of 1, 2, and 3. So they're labeled. I know which point is which, and then I can pin this down. Except it's not the complete picture. So in order to figure out exactly where this triangle is located, it involves solving some equations. So you have a system of polynomial equations to solve. People have solved this one. You can find solutions all over the internet and in books. But the interesting thing that comes up when you try to solve this to figure out the solution is that you find out that there are generally 8 solutions. So you get a system of polynomial equations and there are generically 8 solutions. It turns out that 4 of the solutions will be on the other side of the lines here. So you'll have 4 behind the focal point and 4 in front of the focal point. So in reality, you'll get only 4 in front. That's if you set up lines in your system of equations here. So only 4 in front of the camera. So that means that if I have a fixed rigid triangle and I make a kind of house for it or a cage for it out of these yellow lines, then that means that there are 4 different ways that I could stick that triangle in there so that the vertices of the triangle touch these lines. So you could also try that for a home project if you like. Make a pyramid out of 3 straight sticks and then see if you can fit a triangle in there 4 different ways. So the algebra works out for that. In order to remove redundancy, you just go further. So if we get up to P4P, P5P, there's still some redundancy. Say there's still some multiple solutions. And problems with coplanarity. And this will especially be true in actual systems where you're observing these points in an image due to discretization and noise. You may end up with several plausible solutions that are very close in terms of the image coordinates, but they might be quite far away in terms of the orientation of the triangle. So there ends up also being almost solutions, let's say, or epsilon solutions in this range. And so eventually you get up to P6P and higher. The more points that you observe, the better. And the further away from being coplanar, the better. So this provides greater distinguishing power. So on the Oculus Rift DK2 headset, for example, there are, I believe, about 40 LEDs, and they're distributed all over the place, not necessarily coplanar. So this gives a lot of discrimination power in terms of resolving the position and orientation of the headset when it's in front of the camera. You don't see the LEDs because they're hidden behind infrared transparent plastic. So we cannot see through the plastic, but if you could see in the infrared spectrum, then you would see the LEDs. You could also look at it with an IR camera if you want directly and show the images, and you'll see the LEDs lighting up. All right. Does this make sense? So we get enough information, we get enough equations to solve. I don't want to go into what happens to, how to solve each one of these equations. You start entering into a subject called computational real algebraic geometry. It's sort of like the polynomial generalization of linear algebra. So, linear equation solving using linear algebra. There are whole methods for polynomial system solving. They become very useful in various fields in engineering, robot motion planning, for example. They show up. They also show up here in the case of these kinds of solutions. One thing to pay attention to is we call incremental PNP, which is suppose I'm looking at the image, and in one coordinate frame I have the features, and I have an estimate of the position and orientation, and then in the next coordinate frame I notice that these features move by some small amount, and I can still, I still have my identification going. So these features move by some small amount. All I have to do is slightly update my estimate of the position and orientation, correct? Right, because in one frame time, let's suppose your camera's running at 60 frames a second. So that means your head's moving. It cannot move too far in 16.67 milliseconds. So there's a tiny change in the image here. And all I need to do is figure out what is the change in position and orientation. I have the gyroscope and accelerometer, which I can use as well to make a good estimate as far as how much change there's been in the transformation. And so to do the final bit of correction, I could just perform a very simple local optimization to just perturb this object. I could imagine using the equations of perspective transformation that I'm just perturbing this object in the virtual world that I'm trying to track, which in this case is the head. I'm trying to track the head, and I want to just do a perturbation so that the new position orientation that I'm estimating lines up perfectly with the observation. So I could just proceed in an incremental fashion like this. It's like an incremental optimization where I just do a little bit of perturbation at each step, and it ends up being fairly straightforward because it's not as hard as completely from scratch. I show you the headset, where am I? I have to figure it out by solving the equations from scratch. Once I know the solution, it doesn't change by very much from one frame to the next. So that's what that part is. Questions about that? So that gives me a new measurement now. It's another kind of drift correction information, which is the updated position. So a position estimate that's based on line of sight visibility. So now I can use that again in a filtering method. Let me just give a little bit of a description of how that works. And then we can move on to another tracking technology called Lighthouse, and then I'll be done with tracking methods.